Okay, hello and welcome back. In this video, we will cover section 2.5 on graphing transformations. So it's a technique for graphing complex functions. Last time we were looking at all of what's called the library of functions, or I've used the term the parent functions. So things like simple functions we've seen like x squared, x cubed, the square root of x, absolute value of x. You could add the cube root. What else? Just the standard linear function or the identity function. Um, so all of these you should have a decent grasp on what their graphs look like and maybe a few basic points on the graphs. But oftentimes functions are more complicated, but we can see them as modifications of these parent functions or from the of these functions from the library of functions. So maybe they've been shifted around, um, or they've been stretched or modified in some other way. So we'll see how we can um, start to look at more complicated functions and already tell, even without graphing, what it might look like, what kind of parent function it's coming from, and how it's been modified. And this is extremely useful um, in many domains. So let's get started. So the first thing we'll look at is horizontal shifts and vertical shifts. And these are pretty easy to recognize. So for a vertical shift, it says if a positive real number k is added to the output of a function, and they're just speaking generally, some function f of x, then the graph of the new function would look like whatever. So like consider f of x the parent function. It would look like just that function plus some number. If it's positive, then it's shifted vertically up that number of units, k units, if this number is k. So if it's plus 3, then it's been shifted up 3 units. And then if the number is negative, it says if a positive real number is subtracted from the output of a function, you get something that looks like this, f of x minus k, then the graph is shifted vertically down k units. So that's how you can also call these rigid transformations. It just takes the entire function and it's like you're picking it up and shifting it up or down some number of units, like sliding it across the xy plane. So I have a few inputs here from Desmos. It's a really easy tool to play around with. Let me see if it'll load in. Cool. So here we're imagining we have the parent function x squared, and that's what's graphed here. And I've added this plus k, so that's some number that is being added to the function. And notice it's on like the outside of the function. So anything that's added outside will shift vertically, will shift the function vertically. So you can play around with this slider and see, well, if as k gets larger in the positive direction, it shifts the function upwards. Go up to 10 here. So we'll go back down. If k is equal to 0, then we just get our original function. But then in this case, if k is negative, that means we're subtracting, so it shifts the function down. So you can see it's just a rigid, it's like we're just sliding this function up or down depending on this value of k. So let's practice with a couple quick examples. And we'll keep using x squared. So it says use the graph of x squared to obtain the graph of x squared plus 3. So we can do two quick little sketches. It's always good to first, let's say we are just given this without any context. The first task I would say is to recognize what the parent function is. So it's the squared function that's been modified with a vertical shift up 3 units. That'll usually be our first task. So if I need to graph this, this one's pretty simple, but this is a useful technique as things get more complex. I would start with just a quick sketch of the parent function, just to remind myself of what we're working with. So x squared, that's our parabola centered at the origin. Let me add a couple spaces for units. And I usually keep like 3 good points around. So I know it has the point 0, 0 at the origin. If I plug in 1, 1 squared is 1. If I plug in -1, -1 squared is also +1. So it's useful to have a couple points, especially once we start shifting around and reflecting, then we can work with these points to see where our graph should end up. So 0, 0, 1, 1, and -1, 1. Now we want to transform this into g of x, which is, I'll stick with the blue here, g of x is x squared plus 3. So we have our function, and then we're adding 3 on the outside. It's like going to add 3 to the result of the squared function. So we can imagine this is going to add 3 to every y value on the graph. That's another way of looking at this. So we'll add 3 to every y value. So any y value we see here for these points, our resulting graph, we should add 3 to each of those. And that can help us see if we have um, the right position. But you can also just imagine picking this graph up and moving it up 3 units. So let's create our true graph here. So I'll make a little more space up top because I know it's going up. So I'm already thinking where the vertex will be. It'll be up here at 0, 3 instead of 0, 0. And I know I would go over to the right one and up 1 for my next point here. So instead of 1, 1, this would be 1, 4 because we added 3. And then this would be -1, 4 on the left side. I'll build my parabola. I'll label my points. So 0, 3, 1, 4, -1, 4. So everything's been shifted up 3 units. It also asks us for the domain and range. So the domain is all values from -infinity to +infinity. It goes infinitely in both directions. And then the range, for just x squared, it was from 0 to infinity, but now everything's been shifted up. So notice a vertical shift will affect the range. We can say the range is from 0 to, I'm sorry, not from 0 now, from 3 to infinity. So the range has been shifted up because all y values have been shifted upwards. So that's a vertical shift up. And we can do the same thing going down. I'll try to do it so we can see both here. So now we want g of x being x squared minus 4. So this will be a vertical shift down 4 units. And yeah, when I look at this function, that's what I see. I see, oh, it's the parent function x squared vertically shifted down 4 units. And I can already start to visualize what that would look like and how that would maybe affect the domain and range of the function. So we still have the graph up here, so we can reference that. Let's just jump straight to the graph of g of x. So it's going down, so let me make some space down here. So if we're starting at this graph and we're going down 4 units, then I would expect the vertex to be, it starts at the origin, so it will shift down 2, 3, 4 units. So it should be down here at 0, -4. So notice I'm using these points, these like anchor points to tell me where I should be going. Okay, now I know I'll have a point up 1 over to the right. So at 1, -3, and also at -1, -3. Notice this will also produce some intercepts for us. We could ask ourselves, what are the x-intercepts of this graph? Like where is x squared? Where is x squared minus 4 equal to 0? Well, that's where x squared equals +4, or where x equals plus or minus 2. So I should know that I'm going to have some intercepts here at +2 and -2. My scaling might be a little bit weird here, but it should turn out pretty decent. Yeah. So as we shift graphs around, there might be new attributes that are interesting. Like before, we just had an x and y intercept at the same point, but if it shifts down, it creates two x-intercepts along with our y-intercept at the vertex. So let's label these points. This would be 1, -3. This would be 2, 0, -2, 0, and -1, -3. So we get a couple extra points of interest here. And let me just check something really quick. All right, cool. So let's keep going. So that's vertical shifts. Up or down, you'll see something added or subtracted outside of the function. Now, we could also shift horizontally, either to the left or right. So horizontal shifts. So this is where you would add or subtract something, what I'll call inside the function. And notice you see that in this kind of notation, f of x minus h. Notice the thing is being added or subtracted inside of the function. So that's something to consider, and we'll see some examples here. So this says the graph would be shifted horizontally to the right h units if you have x minus some number h. And then conversely, if you have some number added to x, it shifts horizontally to the left. And this might feel a little bit backwards in logic. If you see something subtracted from x, we're kind of imagining that it would be to the left because that's getting smaller, but it actually shifts the graph to the right. And if something is being added to x, it will shift the graph to the left. So that might take a couple times to get used to. It's a little bit backwards for horizontal shifts. Whereas with vertical shifts, it's a bit more, makes more natural sense. If we add something, it goes up. If we subtract, it goes down. And let's see in this little demonstration here. So this time it's with the square root function. And notice that h is being subtracted inside of the square root. So if we had minus h on the outside of the square root, this would be a vertical shift. But inside, notice it produces this horizontal movement to the right or left. And notice when h is some positive number, meaning like here, this would show up as x minus 4, the square root of x minus 4, it shifts the graph to the right 4 units. Whereas if we're inputting a negative number, like -5, that would make this x plus 5 because you'd be doing minus -5. So if there's a plus inside the function, it shifts it to the left. So if you add to x, it moves it to the left. If you subtract to x, it moves it to the right. Again, might feel a little bit backwards, but you'll learn to recognize it for sure. So a couple quick examples here. So now we want to graph square root of x minus 2. Well, first let's recall what square root of x looks like. Square root function. So I know it has the point 0, 0. The square root of 0 is 0. The square root of 1 is 1. And then I could put the point 4 comma 2. The square root of 4 is 2. That can help me see it's going to produce this sort of projectile-like motion, or it's kind of like half of a sideways parabola. So 0, 0, 1, 1, and 4, 2. All right, so with that in mind, let's graph our actual function, g of x being the square root of x minus 2. So I see 2 is being subtracted from x. So when I see that, and it's inside of the function, it's underneath the square root. So I'll say this should be a horizontal shift to the right 2 units. And it might be helpful to do a little annotation like this in your notes to help you see, especially as we start putting multiple steps together. All right, so let's produce our graph. So it's going to the right 2 units. So imagine picking up this graph and shifting it to the right by 2 units. One, two. So I'm already thinking that's where this like origin point will be moved to. So as I'm doing this, I'm going to already place a point right there. Maybe going 4 units out to the right from that. So I know I should have 1 point to the right of that and above it, because that's what we had over there. So this will be the point 2, 0. So we should have the point 3, 1 here. And then, we can also think about just adding 2 units to the x values here. So that's how I got 3, 1. So that means we must also have the point 6, comma 2. 1, 2, 3, 4, 5, 6, 1, 2. So this produces that horizontal shift to the right by 2 units. And then let's give the domain and range. So the domain here for root x, it starts at 0 and then goes to positive infinity. It's nice to have the graph here so we can visualize. So if it's been shifted to the right, it's going to shift the domain over 2 units as well. So it will start at positive 2 and go on to positive infinity. And then the range has remained unchanged because we haven't shifted up or down. So range is from 0 to infinity. So domain and range. All right, and then we can shift to the left. So let's produce this one too. We'll still reference this graph up here. But now we're looking at g of x being the square root of x plus 4. So my parent function is the square root of x. I see there's a 4 being added inside of the function. So it's a horizontal shift. This will be horizontal. And it's plus, so it's going to go to the left 4 units. So let's produce our graph. So I know I'm going to be going over to the left. 1, 2, 3, 4. That's where the function should start. I'm imagining taking this point and shifting it over left 4 units. You can also imagine subtracting 4 from every x value. So that should be the point -4, 0. Then I know I should go to the right one and up 1. That'll be my next point. So this will be -3, 1. Or I'm taking this point 1, 1 and subtracting 4 from the x value. And then that means for this point 4, 2, if I subtract 4 from x, I'll get 0, 2. That will be actually our new y-intercept. So 0, 2. Yeah, if we plug in 0 for x, we get the square root of 4, which is equal to 2. So connect the dots, get our nice function here. 0, 2. What do we need? Domain and range. So let's say the domain. Now we've shifted to the left. The function is starting at -4 and going off to positive infinity. And then the range, still starting at 0 and going to infinity. Because we didn't do a vertical shift at all, just horizontal. All right, let's combine it all together. Now we're looking at, let me write out the function. So we're looking at the absolute value of x plus 3 minus 5. So the first thing I want to identify is what's the parent function. I see the absolute values, so we should be starting with a base function of the absolute value of x. And then what's happened to it? Well, we added 3 inside the function, inside the absolute values. So this is a horizontal shift. It's plus 3, so it goes to the left 3 units. And then on the outside of the function, we subtracted 5. So this is a shift down 5 units. If you subtract on the outside, it goes down. If you add on the inside, it goes to the left. So could do this in 3 steps. Let's try to do it in 2. Let's first just picture absolute value of x, just to remember what it looks like. It's our V shape, if you remember. So we'll have the point 0, 0, absolute value of 0 is 0, absolute value of positive 1 is 1. We basically get a line going in the positive direction. And then the absolute value of -1 is positive 1, -2 is positive 2, so we get a reflection on the other side. It's like taking a line and reflecting the negative side up into the positive realm of the second quadrant, where y is positive. All right, and let me stick a couple points here. So 0, 0, 1, 1, -1, -1. Cool. So let's try to do both of these in one move. Let's try to be a little bit tricky. I want to move it to the left 3 units and down 5 units. So let's see if we can get it. Probably be somewhere over here. So I'll first just focus on that vertex point. It's starting at 0, 0, so I'm going to go to the left 3 units and then down 5 units. 3, 4, 5. So my vertex point should live somewhere like right here. And this would just be at the point -3, -5. Left 3 units, down 5 units. All right. Do we have any other points of interest? Well, if this is going to be a V shape opening upwards, we're probably going to have a y-intercept and also 2 x-intercepts. We'll have the points like one above and one to the right, just like we had here. So I can get those pretty much for free. We'll have 2 points here. But how about these intercepts? Where are they going to end up? Well, we can find the x-intercepts by plugging in 0 for, or we can find the y-intercept by plugging in 0 for x. So f of 0 would be absolute value of 0 plus 3 minus 5. That's absolute value of 3 minus 5, or negative 2. So I can imagine, yeah, that looks about right. I'll have some point going through there. What about the x-intercepts? Well, we would set it equal to 0 and solve. Set it equal to 0. So I'll add the 5 over, x plus 3, absolute value equals 5. And then recall, to drop the absolute value, we need to consider x plus 3 equals positive 5, or x plus 3 equals negative 5, or like a plus or minus 5. So x would be, and this makes sense, we would assume we would have two intercepts just looking at the graph. So x would be 2, or x would be negative 8. So I'll probably have over here, yeah, that looks about right. Imagining we have our V-shaped opening. Probably not perfect, but looks like it lines up pretty good. And then here, I think my scaling was probably pretty off. 1, 2, 3. This one is probably needing to be more like this. 4, 5, 6. It didn't quite line up, I think, due to my sort of bad graphing. But we solved it analytically, so we know that this point should be negative 8, comma 0. And then this is 2, comma 0. And then we have our vertex negative 3, 5. Oh, and then our y-intercept too. 0, comma negative 2. So a couple points of interest there. And then let's list the domain and range. What's our domain? Looks like from negative infinity to positive infinity. It goes forever in both directions. And then our range, where will that be? Well, it starts down there at negative 5 and goes off to positive infinity because it keeps going upwards infinitely. Cool. Just check something. Okay. So that's just showing we can combine two different movements, and we can add even more too. And now, with this in mind, we can start looking at more complex functions and already start to visualize what it's going to look like. What's the graph going to look like? So pretty cool. All right, let's look at also vertical and horizontal stretches, which they're going to call compressions and stretches. So we were just looking at adding and subtracting inside and outside the function. So this is going to apply to multiplication or division, which we can also view as multiplication by a fraction inside and outside the function. So the first one that they bring up is a vertical compression or stretch. So it says if we multiply some number a on the outside of the function, a times f of x, and if a is greater than 1, if a is just equal to 1, nothing happens. We just get our f of x back. If a is greater than 1, then we get a vertical stretch by a factor of a. And if a is a fraction, that means we're like dividing. So we get a compression. So it'll be squashed or stretched depending on what a looks like. And just to look ahead, the sign of a also will do something too. If a is negative, it will cause a reflection across the x-axis. We would reflect across the x-axis. And then in a similar way, we have horizontal compressions or stretches. This is when we multiply something inside the function. And we see that here, y equals f of a times x. Notice that a is inside. So if a is greater than 1, then we get a horizontal compression, which looks similar to a vertical stretch. It compresses it inwards. And if a is a fraction, then we get a horizontal stretch. And these can be somewhat tricky to visualize. But let's look at a Desmos graph. Oh, and also similarly, if in this case they're still using a, I'm going to use b in my examples um, just to show a difference between them. But here, specifically since they use a, I can say in this case, if a is less than 0, if it's negative, you get a reflection across the y-axis. So let's see what I mean by that. Let's load this up. So another graph. So this time I'm looking at the square root function, and I've inserted a new parameter on the outside, which I'm calling a, and then inside the function calling b. So let's first focus on a. So if a becomes positive, it stretches the function vertically. It stretches it up. And let's go back down. And notice what happens as we get less than 1 but greater than 0. So down to 1. So that is a compression now. It's squashing it. So this is its original position. If a is greater than 1, it stretches it. If a is between 0 and 1, it like smushes it down. And then notice what happens as we go into negative. It flips it across the x-axis. That's the reflection part of that. And the more negative, the more it gets stretched in that direction. So see this kind of movement that this number does to the parabola. If a is 0, it flattens it out completely, which makes sense. Flattens the function. Or we stretch the function in the positive direction, or we flip it to negative and stretch it in that direction. So pretty cool. And then for b, this is inside the function. Let me bring a back to 1. For b, if b is, this is technically a horizontal compression. It's squishing it in horizontally, which visually ends up looking a lot like a vertical stretch. Then as b gets closer to 0, it will also flatten it out. But then negative, notice it flips it across the y-axis. So slightly different behavior. Negative, positive, negative, positive. So keep in mind which axis would be reflected if you insert a negative either on the x inside or outside the function. So let's see some written examples. Let's do a couple test graphs. So starting with the square root of x, let's draw that back in. So now I will have, and I'll just do a sketch. Start at 0, have the point 1, 1, and have the point 4, 2. So 0, 0, 1, 1, 4, 2. All right, so we are finding g of x, which is 2 times the square root of x. So another way you can visualize this is every y value will get multiplied by 2 because the output of the function gets multiplied. So all y values are multiplied by 2. So if you have these points ready to go from our parent function, we can just think about multiplying every y value by this number. And that's going to produce that vertical stretch type of behavior. So this time we still keep the origin point because 0 times 2 is still 0. 1, 2, 3, 4. 1, 2, 3, 4. So instead of the 0.11, I should have the 0.12. The y value is multiplied by 2. And instead of the 0.42, I should have the 0.44. And this will produce that vertical expansion as we go out. So let's label these 0, 0, 1, 1, 4, 4. It didn't ask us for the domain and range, but we could still consider it. And notice nothing has changed from that perspective in terms of the domain and the range. However, you could say the rate of change of the function has increased if you think about how quickly the values are increasing. That's something you'll think a lot about in calculus. How is the function changing as x changes? How quickly does y change? Is it slow or is it fast or somewhere in between? All right, let's look at one more example of a compression. This time we're starting back with the absolute value function. So we're switching up the functions just to show that this applies to functions in general, not any specific one. So if you learn these patterns, you can view any function and see, oh, it's been flipped, stretched, rotated, moved around. So a quick sketch of absolute value of x. That's our v shape. Let's take a couple points here. So now we got 0, 0, 1, 1, and negative 1, 1. Sometimes my pen gets like more goopy for some reason. Kind of strange. Okay. So what are we graphing? G of x. So g of x is 1/2 times the absolute value of x. So we're still going to multiply all of the output values by 1/2, or we can view that as a division. We'd say each y value is, in this case, divided by 2. So this is effectively going to like flatten the graph. 1, 2, 3, 1, 2, 3, 2, 3, 4, 1. All right. We'll still have the same vertex point at 0, 0, because 0 divided by 2 is still 0. And then instead of 1, 1, I should have the point 1, comma 1/2. And similarly, I should have the point negative 1, 1/2. Think about dividing these two y values by 2. And you can see this will produce a wider V shape. So it flattens it out. So that's vertical, and we just graphed vertical compressions, but you can apply the same thing to horizontal compressions as well, and expansions. So that's multiplication. Multiplication stretches or compresses the function, whereas addition, inside or out, will shift it rigidly up and down or left and right. All right, and I mentioned this reflection aspect of multiplying on the inside or the outside, so let's just see these on their own specifically. So it says it will reflect across the x-axis if the function is multiplied by a negative 1. So if we see a negative multiplied by the whole function. And then it reflects it about the y-axis if we see x being multiplied by a negative. Notice the negative is inside the function. So let's look at these two. Our first one is negative x squared. Well, we can first do just a quick sketch of x squared. Should be pretty used to this one. So we got vertex at the origin, the point 1, 1, negative 1, 1. This one is curved, so a nice parabola. I'll label my points. And if we are doing, I'll call this one g of x, negative x squared, we can think, just like with a stretch multiplying all the y values by something, we're just flipping, changing the sign of all y values. So imagine multiplying all of the y values by negative 1. So that will effectively mirror the image across the x-axis. So let's draw it out. I'll still have the same point at the center. Because that stays put. Because negative 0 is just 0. So instead of the point 1, 1, I would have the point 1, negative 1. The y becomes negative. And instead of negative 1, 1, I will have negative 1, negative 1. The y becomes negative. So this gives us the downward facing parabola. So let's label these 0, 0, 1, negative 1, negative 1, negative 1. And it wants the domain and range. So the domain is still all real numbers, negative infinity to positive infinity. And the range, instead of going from 0 to positive infinity, we're going to go from 0 to negative infinity. So it reflects the range. It flips it around. So from 0 to negative infinity. So we get a reflection across the x-axis. That's when you see a negative outside of the function. All right, example 10. Notice the negative is inside now. And it's the square root of x. Let's first imagine just the regular root x. I've done this a few times now. Just do a quick sketch. 1, 2, 3, 4, 1, 2, 1. So it has the point 0, 0, 1, 1, and 4, 2. Add that back in. Now this x inside, or this negative inside, well, it's going to flip the sign of all of our x values. If we plug in a negative 1, it's going to make it positive 1. If we plug in a positive 1, it's going to make it a negative 1. So you can think about your previous graph and then multiply your x values by negative 1. And that will cause the reflection across the y-axis. So this is probably going to go leftwards now. 1, 2, 2. We'll still have the same origin point. Instead of positive 1, we would get negative 1, positive 1. So the x becomes negative. And then instead of positive 4, 2, we would get negative 4, positive 2. When in doubt, you can always create a little table of values. You can imagine x values, and then what would be the square root of negative x? Well, 0, that would be 0, 1, square root of Well, here we can't. Notice now 1 is not in our domain anymore, because then we'd have the square root of -1. It should be imaginary. So we have to plug in a -1. This will be negative, -1, +1. There's our point. -1, +1. So you can try just plugging in some values. If we plug in -4, that gives us square root of 4, which is 2. And there's our point, -4, +2. Yeah, so now don't be afraid to make a little table if you're ever unsure where your points should go. All right, so let's bring it all together. They give us a nice summary. So if we add or subtract outside the function, then we're shifting up or down. So that's vertical. If we add or subtract inside the function, then we're shifting to the left or the right. That's horizontal. If we multiply outside the function, then we stretch vertically. It's a vertical stretch or compression. If we multiply inside the function, then we stretch or compress horizontally. So there's that general theme of inside the function horizontal because it's affecting the x values, and outside the function vertical because it's affecting the y values. And then if there's a negative on the outside, it reflects across the x-axis because all the y values become negative. Or if they were already negative, they would become positive. And then reflection inside, we would shift across the y-axis because all the x values are either shifting to negative or shifting to positive, depending on their original sign. So I like to write like one big combined notation just to sum all of this up. So we have some function, and we could multiply something by x. We could shift it horizontally, we could multiply something outside, and we could add or subtract something outside of the function. So this will give you the vertical stretch or the x-axis reflection if it's negative. This b will give you a horizontal stretch or a y-axis reflection. Adding or subtracting inside gives you a horizontal shift. And then adding or subtracting outside gives you a vertical shift. So you can apply this to any function, and later on we'll apply this to the trigonometric functions also. We can imagine stretching them, flipping them around, compressing them, shifting them, that sort of thing. So let's combine this all together. I think we got two or three examples involving multiple steps. The first one just wants us to build the function. So it says we're going to start with y equals the absolute value of x. You can imagine that's like step 0. That's our parent function. And what does that look like? I'll just do a super quick sketch. Something like that, our V shape with a vertex at the origin. Then for step 1, they want us to shift left 2 units. So it's a horizontal shift to the left. And recall with horizontal shifts, it's a little bit flipped in logic where if it goes to the left, we would be adding inside the function. So inside the absolute value, I'll do x plus 2. That will shift me to the left. Let's do a quick sketch. 2 units, and then some V shape. Then they want us in step 2 to shift up 3 units from our previous step. So let's just take where we were and go up 3. So I might have to be a little bit more detailed, but I know I went to the left 2 units and then up 3 units. So that's where the new vertex should be. So it's up there somewhere. And in the last step, we want to reflect about the y-axis. And we said to reflect about the y-axis. Oh, and let's add our equation here too. This would be y equals absolute value. We had the absolute value of x plus 2. That was our shift to the left, and then we went up 3 units. So we would add 3 on the outside of the function. Outside of that. Cool. Now if we reflect about the y-axis, this will be our final function. That's where we would add a negative in front of our x. That causes the reflection. It turns all the negative x values positive. So let's do that. So reflecting across the y-axis. So maybe I should label a couple points here. This was the point -2, +3, because we went left 2 units, up 3 units. So that means we should have another point here at -3, +4, to the left 1, up 1. And then same thing on the right side, -1, +3. So I'm going to take all of those x values and just make them positive. That's what that negative does inside of the function. So instead of -2, +3, I should have +2, +3. That's where the vertex will be. And then instead of -3, +4, I should have +3, +4. And then instead of -1, +3, I should have +3, +3. I'm sorry. It's because I distracted myself. +1, +3. Instead of -1, +3. So this is the absolute value of x that's been shifted to the left 2 units, up 3 units, and then reflected across the y-axis. So let's label these points too. 2, +3, 3, +4, and 1, +4. I think I kept saying 3. It's 1, +4. Yeah, apologies for that. +1, +4. It's my own mental distraction. Gotta stay focused when we're doing math. All right, maybe I'll box this too. Should have a single pointed mind when we are working through this kind of stuff. All right, let's look at another example. This one didn't ask us to graph it, but it's helpful to view as we build the equation. But that's one kind of homework question that you'll see. They'll give you some description of a function and some parent function, and they want you to build the equation. but they might give you the equation and ask you to build the graph. So let's do that. And I'm gonna use a technique called like what we did here. We did a series of transformations. We started at what we know and just did step-by-step little movements until we have our final graph. You might be able to do it all in one once you get a good handle on this, but it's easy to make little mistakes for sure. So let's look at this one, this peculiar function. We haven't done a rational function yet. And it might not be obvious, but this parent function, it's some shifted transformed function of, I'll just say y for now, of 1 over x. Because we have an x in a denominator. This, I might write it out as, if we pull this 3 out in front, which we can, it might be easier to see all of our transformations. So even without looking at it, what's happening to this graph? Well, something's being added on the outside. So that's a vertical shift. It's positive, so it's going to go up 1 unit. Something is being subtracted from x inside the function. So that's horizontal, and since it's a minus, it will go to the right 1 unit. And then this 3 is being multiplied outside of the function. So this is a stretch by a factor of 3. So all the outputs will be multiplied by 3, and then 1 will be added to them. So it's going to be stretched and shifted. So let's build this step by step. It's kind of hard to visualize it all at once. So let's start with the parent function. And let's just do a quick sketch. So recall this function has 2 asymptotes. It has a horizontal and vertical asymptote on the axes because we can't input 0. We would be dividing by 0. And the function will never be equal to 0, at least in its current state, because there's nothing we can plug in that will make 1 over x equal to 0. And 1 over 1 is positive 1, and 1 over negative 1 is negative 1. So we get those 2 points. And remember, since we have asymptotes, it's going to do this curving behavior. So if you recall, the graph looks roughly like this. Let's say this is the point 1, 1, and negative 1, negative 1. So that's our first step. So let's kind of follow what's happening to x. There's this minus 2. So that can be our second sketch. Let's consider 1 over x minus 2. Just one transformation at a time. Well, this is going to be a shift to the right by 2 units. I wrote 1 unit up here. Definitely should be 2. 2 units. So we'll shift to the right by 2 units. All right, sorry about that. So I'll still do a sketch. It's going to the right, so I still have the asymptote on the x-axis. But then this asymptote on the y-axis gets shifted as well. 1, 2. You can imagine 2 units it gets shifted over. So I can imagine adding everything to my x coordinates. So instead of 1, 1, this should be the point 3, 1. So I should have some point here and a symmetrical point over here at 2, negative 1. Or no, I'm sorry, at 1, negative 1. So that would be 1, negative 1. So some kind of curved shape like this, and then a curved shape like this. Just doing rough sketches here as we go through the transformations. All right, let's jump up here. So now let's throw in the vertical stretch. We're going to take what we just had and multiply all the outputs by 3. So on that same graph, all the y coordinates will be multiplied by 3. So we'll still have that asymptote at x equals 2. Still have the asymptote on the x-axis. And then instead of the point 3 comma 1, I should have the point 3 comma 3. Imagine multiplying that y coordinate by 3. So 1, 2, 3, comma 3, some points up here. So that will produce a more stretched out curve. And then instead of negative 1, negative 1, instead of 1, negative 1, we would get 1 comma negative 3, multiplying the y output by 3. And then we'll get our curve like this. Notice we pick up a y-intercept. Let me make this a little bit smaller just to save the room here. All right, now we just need our vertical shift. We have that +1 on the outside of the function. So let's make our final graph. So this is f of x, the full thing. I'll go ahead and stick the 3 back up top, x minus 2 plus 1. Let's draw it over here. So now imagining everything is going to shift up 1 unit. With these, it's helpful to draw your asymptotes first. So I still have the asymptote at x equals 2. And instead of the second asymptote being on the x-axis, since everything has shifted up 1 unit, it will now be going through the horizontal line y equals 1. And now I'm going to imagine taking my previous points and adding 1 to every y value. So instead of 3, 1, I should have the point 3, 2. 1, 2, 3, 1, 2. Oh no, I'm sorry, I'm looking at the wrong graph. I need to look up here. So instead of 3, 3, I should have the point 3, comma 4. So 1, 2, 3, 1, 2, 3, 4. Yeah. And then that will be our curve. So 3 comma 4. And then our second point up here, we said that this was positive 1, negative 3. So it should be the point positive 1, negative 2 now. And then we'll have some kind of curve. Notice we have an x and y intercept. Just curious what those would be. Well, we can find y-intercept by plugging in 0 for x. This would be 3 over 0 minus 2 plus 1. So negative 3 halves plus 2 halves. Negative 1 half. And that looks pretty good. That's like, yeah, right in between. Negative 1 half. And then just curious, how about x-intercept? And I'm just doing this for fun, but let's see. So 3 over x minus 2 plus 1, let's set it equal to 0. Subtract the 1 over, 3 over x minus 2 equals negative 1. If we multiply the x minus 2 over, it's going to hit the negative 1 and flip the sign of everything. So negative x plus 2. And then If I add the x over to the left and subtract the 3, I get x equals 2 minus 3, which is negative 1. Which, yeah, that worked out pretty good. There it is, negative 1. Sometimes I don't trust the graph because of sketchiness, just I might not have spaced the intervals of the units perfectly, but this worked out pretty nicely. So you can always do that too to test if your graphing is working out. So I'll just label this point here. This is, I'll stick with the blue, 1 comma negative 2. So it did want the domain and range. Let's throw that in here too. So my domain is, I'll use set builder notation now because I want to say everything except a single value. This will be a little bit more compact because I want to not have this asymptote value where x equals 2. So I'll say all values x such that x is not equal to 2. And then similarly for the range, it's all y values except for y equal to negative 1, positive 1 I mean, because we have that asymptote. All values y such that y is not equal to positive 1. And you can get this domain by thinking what will cause that denominator to equal 0. Well, if x equals positive 2, I would get 2 minus 2, so I'd have to divide by 0. And then if you remember rules of horizontal asymptotes, you can apply that here to see that y should not equal positive 1. Well, you might have to first combine this into a single rational function. So that's a little bit tricky. It's useful just looking at the graph. All right, so sorry this got a bit messy. But this is the technique of graphing by a series of transformations, doing one at a time until you have your final graph. So let's see one more example of this. And I'll try to be a bit neater. Okay, so what is our function? We have f of x equal to the square root of 1 minus x plus 2. It might be helpful to flip that subtraction around to view it as the square root of negative x plus 1. You can do that. Plus 2. This might be helpful to view our transformation. So we can see that there is a shift up 2 units because we have plus 2 on the outside. We're adding 1 on the inside, so there should be a shift left 1 unit. And then there's a negative inside on the x, so that is a reflection across the y-axis. So let's do it as a series again. What's our parent function? Well, we have a square root, so that's where we'll start. Just y equals the square root of x. And we've graphed this a few times. I'm going to be a little bit more intentional. So I have the point 0, 0, 1, 1. Could add 4, 2. We'll stick with these for now. All right, now let me just make a point here because this was a bit confusing for me. If you have both a reflection and a horizontal shift, I'm going to recommend doing the horizontal shift first and then doing the reflection across the y-axis. Otherwise, you might get into trouble. So first do the shift and then reflect. So let's do the shift first. Let's imagine we have the square root of x plus 1. Shift it to the left 1 unit. So just a rigid transformation to the left, so that starting point would be over here at negative 1, 0. Then instead of 1, 1, I should have the point 0, comma 1. So shifted to the left. Now let's do the horizontal reflection. Or I guess you could say this is a vertical reflection. We're reflecting across the y-axis, so in a horizontal direction. So negative x plus 1. So that's going to flip all the x values from negative to positive. It's going to flip the direction. Imagine this rotating. So I will have, it'll point to the left instead. So instead of negative 1, 0, I would have the point positive 1, 0. Instead, well, for 0, 1, I would still have 0, 1 because negative 0 is just 0. But let's say I had the point 1, 2, 3, like 3, comma 2, because that would be on it. I would then get negative 3, comma positive 2. So that third point might help with the visualization. And then we just need our vertical shift up. So that will be our fourth piece here. This will be our full function. Square root of 1 minus x, or negative x plus 1 plus 2. So I'm going to add 2 to all of the y coordinates of my previous graph. So instead of 1, 0, I should have the point 1, comma 2. Imagine going straight up. Instead of 0, 1, I should have the point 0, 3. Instead of negative 3, 2, I should have negative 3, 4. My scaling is pretty off on this one. This should be probably, oops, more up here. 1, 2, 3, 4. Oh, and then this point. Yeah, that's more like 2. I should put this over here. That'll produce more of the curve that we're looking for. So let's say this is negative 3, comma 4. All right, still kind of a rough sketch, but we got our points labeled and we got it going in the right direction. So let's list our domain and range. Our domain, it's nice to have the graph to look at it, so that's part of why this technique is very useful. So domain in this case, it goes all the way to negative infinity and stops at positive 1. And then the range, yeah, this point should have been more like up there. Let me fix this while we're looking at it. Must have gotten it flipped in my mind. Yeah, 1, comma 2. I think I made it look like 2, comma 1 at first. There we go. So the range going from positive 2 up to positive infinity. All right, so this will be our final graph. Yeah, in that last step we added 2 to all the y values. So 1, 2, 0, 3, and negative 3, 4. Cool. So this was all about graphing transformations. So we did vertical and horizontal shifts. We did compressions and stretches, and reflections about the axes. So there's a nice summary table in the text. It's a good thing to reference. Maybe you can have it printed out. But now that we have these patterns, then we can look at a more complicated function and start to see, oh, it's just this one parent function. It's been shifted to the left or up. It's been reflected and stretched. We can kind of visualize it already. All right, that's it for this video, and I'll see you next time.